Fine. Types of radiations. There are three: alpha, gamma, beta, and gamma. Okay, so alpha is an alpha particle is actually a helium nucleus. I need to explain that. Do you have an idea of that?
Yeah.
Okay, you know that an alpha particle is a helium nucleus.
Yeah.
So it consists of 2 protons and 2 neutrons. It's not a
I thought it was 4 and 2.
Yeah, it's 4-2. Yes, you're right. It is 4-2. That's the notation. The scientific notation is 4-2. That 4-2 means 2 protons and 2 neutrons. So we need to explain that properly. So an alpha particle is a helium nucleus consisting of 2 protons and 2 neutrons. So it's not a helium atom. A helium atom will also have 2 electrons. It's a helium nucleus. Okay?
Yeah.
Alright, so you're right. The notation is 4-2 because it has 2 protons and 2 neutrons. So the notation will be helium. There are many ways you can represent it. Helium. If something has 2 protons and 2 neutrons, what's the mass number?
4.
4. So that's why it's 4. What's the proton number?
2.
2. That's why it's 4-2. Okay. So that's 4-2. Helium nucleus. So you can represent an alpha particle like this, or you use the proper notation of an alpha, which is something like this.
Like what?
What I just wrote.
You didn't write anything on my side.
You've seen it?
No,
No, I'm
you
on the
haven't
next
got-
page. I'm on the next page. I told you to go to the next page. 4-2 like this. It's the same thing. Okay? Is that fine?
Yeah.
Alright. How is it different from a helium atom?
How's what?
I want to hear you more clearly. You say
How's what?
how is an alpha particle different from a helium atom?
Because the alpha particles, the nucleus, not matter.
Are you saying that an alpha particle is just the nucleus of a helium, not the entire atom? You know, a helium atom has 2 neutrons, 2 protons, and 2 electrons.
Yeah.
A helium atom has what?
2 neutrons, 2 protons, and 2 electrons.
Good. But the nucleus of a helium is just 2 protons and 2 neutrons. So an alpha particle is not a full helium atom, but just the nucleus of the helium. Okay?
Yeah.
So that's why an alpha particle will have what kind of charge? What will be the charge of an alpha particle? Yes, what's the charge of an alpha particle?
Plus.
What's the charge?
+1.
It's positive because it has 2 protons,
+1.
positively charged. Because it has 2 protons, it is positively charged.
Yeah.
Okay. So with a +2 sign, 2 plus, or +2 if you like, because of the 2 protons it has. The neutron has no charge. It has 2 protons, so it's positively charged. I'm saying all of this to explain something to you. You know, I was trying to use an example in the previous section of the class, that if you have, for instance, carbon 14. Carbon 14 is an isotope of carbon. You know what an isotope is?
Yeah.
Okay, so carbon 14 is an isotope of carbon. This is the notation of carbon 14, C14 6. All carbon atoms have 6 protons, so their proton number is 6. But they can have different nucleon numbers. Of course, you know, when we write this, the upper one represents the mass number or nucleon number. The lower one represents the proton number or atomic number. You remember, you know all of that.
Yeah.
Okay, so you also told me that if it has 14 as its nucleon number and 6 as its proton number, what is the number of neutrons?
8.
8. Okay, because nucleon number, which is mass number, is neutron plus proton. Neutron plus proton. And since you have 6 protons, there has to be 8 protons, so that you have 6 plus 8 to give you 14, which is the mass number or the nuclear number. Alright. We've done this before. I think it's in our previous. Alright, that's that. Okay, so if carbon 14 undergoes an alpha decay, what will it become? Remember I told you that during an alpha decay, 2 protons and 2 neutrons come out. So whatever is formed will become what? Let's call it, let me call it Y. Or I can use a different letter. I just call it Q. This Q that is formed, what will be its, of course, with an alpha particle. So let's just write the alpha particle so that we know we have all of them. What's the notation of an alpha particle? 4, 2, isn't it? So this Q will have what as its mass number? And what will it have it as its proton number?
16.
Did you say 60?
16.
16?
Yeah.
Should it be 16? Remember,
Wait.
part of the neutrons will come out, and also some of the protons will come out. How many for an alpha particle, how many protons will come out?
2.
How many neutrons?
2.
So what will be left for the mass number in this daughter? 10. So it will drop down to 10, because by the time you have 2 protons and 2 neutrons and 2 protons, that's already 4 nucleon numbers. 4 nucleons. 4 nucleons. So it will become 10. So what will be left for the atomic number? 4. So it will reduce by 2, because 2 protons will go out, and the lower one represents the number of protons left. So it will become 4. The implication of this is a different kind of element will form, right? Because this element has an atomic number of 4, so it's no longer a carbon. It's a different kind of element. During an alpha decay, a different kind of element forms, and an alpha is released. A different kind of element with a different atomic number. Okay. In fact, if this happens in real life, this should be beryllium. Beryllium, because beryllium has an atomic number of 4 if you check your periodic table. Okay, so generally, what the general rule is this: if an element X decays by alpha, assuming it started with a mass number of A, an atomic number of Z, if it decays by alpha, whatever is left, let me call it Y, we now have a mass number of what?
And what? I don't.
Okay, I said this element, this nuclei, which is X, initially had a mass number of A, that's nuclear number of A, and atomic number of Z. Good. So if it undergoes an alpha decay, what will it become?
A minus 4.
Good. So it becomes A minus 4 because A will drop by 4 because an alpha particle has 4 up here. So the nuclear number will drop by 4. The atomic number Z will become what?
Z minus 2.
Z minus 2. Okay. So that's the general rule. In fact, the mass number will balance, the atomic number will balance. So plus this alpha for 2. Sometimes there could be 2 alpha particles. If you have 2 alpha particles, like, do you understand what I mean by 2 whole alpha particles? Anyway, let me not say that I might end up complicating it, so don't worry about that. Okay, so this is the general rule for an alpha decay. Let me zoom it in a bit. For an alpha decay, this is what you get. This is a general rule. Okay. Do you remember some of the characteristics of alpha particle? Like, I'm listening.
And it passed through lead.
They're what?
And it passed through lead. Something like that.
Okay, let me write characteristics of an alpha particle. Well, an alpha particle is the most massive, highest mass. I'll just use some bullet points. Highest mass of all the 3 radiations. It has the highest mass. It's the most massive of all of them. It is most ionizing. You know what it means to ionize?
Most.
Ionizing.
It
To-
releases the most. Actually, I don't know.
Most ionizing. Ionizing simply means it knocks out electrons from atoms of air particles, for instance. Let me just say atoms of particles in its way. Let me just explain it. You see, when an alpha particle is moving, right?
Yeah.
Some atoms of particles that are in its way will be forced to lose electrons because the alpha particle will knock out the electrons from those atoms. So if an alpha particle is moving through air, air particles in its way, where the direction is moving, will lose the electron because it knocks out the electrons from the atomos shell. So when an object loses an electron, what does it become?
It becomes
Yes,
positive.
when an object loses an electron, yes, it becomes positively charged. So it becomes ionized. That's what we call ionizing. So alpha particles are the most ionizing because of their mass. They are the type of radiation that can easily ionize matter in its way because they knock out the electrons from the atomos shell of those atoms and cause them to become ions, positively charged. So can you list the 2 characteristics I've written down?
I what?
The two characteristics I've written down for alpha particles. Can you list
Yeah,
them?
what about them? Do you mean can I write it or?
Now I'm asking, yes, what I've written on the screen. Okay, just read them out before I go to.
Highest mass, most ionizing.
Yes, highest mass, most ionizing. The next one I will talk about is the least penetrating. Is the least penetrating. It doesn't move far and then it is stopped. In fact, an alpha particle can be stopped by a few centimeters of air. It may not move from where you are to the next room, just through air. Air can stop it. It's not as penetrating as the other particles. Did you get that?
Yeah.
And of course, a few centimeter thick paper can stop it. Like the paper you use, your even less than the thickness of your book. An alpha particle may not pass through your entire thickness of your book. A few centimeters of air, a few millimeter of a millimeter thick paper can stop an alpha particle. So it's the least penetrating. Of course, you know it has a positive charge, right?
Yeah.
It has a positive charge of 2. Of 2 plus. So because it has a positive charge, it is deflected in an electric field.
Is what?
Just a moment. Because it has a positive charge, it is deflected in an electric field. Did you hear that?
Yeah.
In fact, because it has a charge, it will be deflected in an electric field.
Yeah.
Okay, it is deflected in an electric field. And in a magnetic field. So let me just complete all that. Read what I wrote in number 5.
It is deflected in an electric field and in a magnetic field. This is because it has a charge.
Yeah. The other characteristics, but I think we just work with this. Alright, that's about an alpha particle. I need to take this further so that you'll be able to answer the question that you have there. Go to the next page. Let me describe beta particle before we answer that question. Remember I said an alpha particle consists of 2 protons and 2 electrons, 2 protons and 2 neutrons. Is that okay?
2 protons. Beta or beta?
I'm talking about alpha. I'm reviewing what I said about alpha before I look at beta.
Oh, yeah.
An alpha particle. Just a moment, please. So an alpha particle consists of 2 protons and 2 neutrons. Yes. Now a beta particle is different. This is how a beta particle. There are actually 2 types of beta particles. There's one we call beta plus and beta minus. The most common one is the beta minus. So let's talk about the beta minus first. right?
Yeah.
So beta minus, because this is what you need to be able to answer that question, beta minus. In a beta minus, this is what happens. You will do that in more details at a higher level. But for the meantime, I'll just explain to you that a beta minus decay occurs when a neutron, I think I need to write that down first so that when I'm illustrating it, you will understand. I'm writing it down. Read what I wrote.
This occurs when a neutron in the nucleus changes to a proton and releases a fast-moving electron called a beta particle.
Let me use the term massless. We say massless. Okay, so you can read the full thing.
Pardon?
You can read the full thing now.
This occurs when a neutron in the nucleus changes to a proton and releases a fast-moving electron called a beta particle, and an almost massless particle called an
Antineutrino. Okay, so this is how a beta minus occurs. A neutron in the nucleus changes to a proton, and in the process it releases a fast-moving electron, which is called beta particle. Of course, beta minus particle. So I have to specify beta minus particle. That's why I'm writing the minus on top of it. Beta minus particle and an almost massless particle called antineutrino. So what it means is a neutron, this is a neutron, let me call it one neutron, changes to a proton, one proton, did you see that? And also releases one electron, which is called the beta particle. Or if you like, you can call it that beta particle. I need to zoom this in. Beta particle. Are you still there?
Yeah.
And then something else comes out, which we call antineutrino. All right. Yep. So the notation of a beta particle, beta minus, the notation, since it is an electron, since a beta minus is an electron, are you listening? Are you listening to me?
Yes.
The beta minus is an electron. So what should be the, do you know the notation of an electron?
Pardon?
the notation of an electron, just like we have the notation of
Pardon?
what is the scientific notation of an electron? What's the mass number of an electron? 0. Atomic number -1.
Yeah.
Do you have an idea of what I just wrote? Not really.
Beta minus decay.
Pardon?
Beta minus.
Okay. Let me explain it briefly. First of all, do you agree that the mass number of an electron is 0?
Pardon?
Do you agree with me that the mass number of an electron is 0?
Yeah.
Because it has no proton, it has no neutrons. No protons, no. What's mass number, by the way? What's mass number? Which is also nuclear number. How do you get the mass number or the nuclear number? How do you calculate it?
Protons plus electrons.
Yes, protons plus neutrons gives you the mass number. Protons plus neutrons gives you the mass number. Since an electron has no proton, it has no neutrons, the mass number is 0, right?
Yeah.
And also, an electron has a negative charge. That's why the proton number, as it were, is -1. So this will be the notation of an electron. 0 for mass number, -1 for proton number. So you can represent a beta minus particle like this, or you use this symbol.
Yeah.
Because I told you a beta minus is a fast moving electron.
Yeah.
Can you read this again? So it can make sense now with the illustration I've given you.
This occurs when a neutron in the nucleus changes to a proton and releases a fast moving electron called a beta minus particle and almost massless particle called a neutrino.
A neutrino. So one neutron changes to a proton, and then it releases a fast moving electron, which is the beta particle, and also that's the word is also a fast another particle which has no mass, or which is that the mass is so small that it's difficult to detect. In fact, it was just recently that the antineutrino was discovered, because of the mass is very, very small, insignificantly small. So it was difficult to detect an antineutrino.
Yeah.
Okay, so that's how a beta minus occurs. A beta minus occurs like this. Okay, please, all of this is to help you understand how to write the notation. So if an object releases a beta minus, I don't want to go to the next page. Let me explain all these things here, so I don't have to be coming back to this page. During a beta minus decay, let's start with our element X that has an atomic number of A. Sorry, we usually use a mass number of A, an atomic number of Z. If it decays by releasing an electron, which is a beta particle, and forms Y, remember plus that beta particle, you can represent the beta particle with this or this.
Yeah.
What will you have for the mass number of Y and for the atomic number of Y? Mass number of Y will be what?
A.
Why will it be A?
Because it has 0 mass at the beta.
Because at the beta particle has 0, so it didn't lose anything for mass number. What will be the atomic number for Y? I'm listening.
Would it be Z minus 1?
Do you think it should be -1?
Z add 1.
It should be Z add 1. That's Z plus 1. So during a beta decay, the mass number stays the same, isn't it?
Yeah.
But the atomic number does what?
Increases.
By 1. So it changes to a different element altogether. This is a different element. Once the atomic number changes, it's a different element. It occupies a different position in the periodic table, so it's a different element. It has a different chemical property. All right. That's for a beta minus decay. The simple rule is 1 neutron changes to a proton, and then a fast moving electron is released, which is a beta particle, and then an antineutrino. That means in a neutron you have a proton and an electron and then the antineutrino, all inside a neutron. Does it not make sense?
Yeah.
Okay. So can I give you a simple example?
Yeah.
Anyway, before that example, let's talk about beta plus. There are 2 beta. So the next one will be beta plus B. Go to the next page. I'm writing about beta plus. By the way, beta plus is represented by beta with a plus on top. Beta, we are now talking about beta plus. In a beta plus, 1 proton, this one is about a proton. Are you listening?
Yeah.
1 proton changes to a neutron and then releases what we call a positron. Okay, which is a positively charged electron. Could you believe that there could be an electron that is positively charged?
Oh yeah.
And then a neutrino. Let me write it. Positively charged. I write the name before I write what it means. So let me zoom in a bit. And of course that's called positron, which is a positively charged electron. Did you see that?
Yeah.
So that positively charged electron is represented with this symbol. So of course the positron is an electron with an opposite charge. So it is still an electron, but instead of having minus, it has a plus 1. Then zero, still a mass number of 0.
Yeah.
Or you can represent it as beta 0 plus 1. So this is a positron, is the what we call antiparticle of an electron. I don't want to go too far. An antiparticle is a particle with the same mass but a different charge. It has the same mass, 0, same mass number, but different charge from a proper electron. What's the charge of a proper electron?
Minus.
-1. But what's the charge of a positron?
Plus.
Now, like I said, if you were to get deeper in this, there's what we call an annihilation, like to annihilate something. When a positron meets an electron, they destroy themselves, annihilate each other, forming a gamma. Yeah, you need to know that. You need to know that because we're going to gamma. You need to even know that. You need to know that. That's actually how a gamma ray can be formed. An annihilation of a positron and an electron. Okay, so that I don't mumble up all of this. I said a beta plus is formed when 1 proton changes to a neutron
Yeah.
and a positron, which is a positively charged electron, also releasing almost a massless particle called a neutrino. This one is called neutrino. The other one is called antineutrino. In fact, a neutrino is an antineutrino is the antiparticle of a neutrino. I'm trying to limit the extent I go in this to make it easier for you to assimilate. Okay, all right. So generally, during a beta plus decay, for a beta plus decay, what's the general notation? If it starts with X, having a mass number of A, an atomic number of Z, and then it forms Y, having what we're going to know, plus a beta plus 0 plus 1. So what do you think we're going to have here for X, for Y, for the mass number? Mass number will remain A. The atomic number will become what?
Z minus 1.
Z minus 1, okay. So very quickly, because we need to cap this. Very quickly, what are the characteristics of a beta particle? Characteristics of a beta particle. Generally, beta particle, not just beta decay, both beta plus and beta minus.
It has.
So let me concentrate this characteristic on beta minus because it's the most common one. Characteristic number 1 is negatively charged, right?
Yeah.
Because it's an electron negatively charged with a charge of minus 1. Number 2, it is less massive than an alpha particle. Which one has the highest mass?
Alpha.
Alpha. So it's less massive than an alpha particle. Number 3, it is more penetrating than an alpha particle. But of course, less penetrating than gamma. Gamma is the most penetrating of all of them. We look at that very quickly as we draw this to a close. Number 4, it is more penetrating than alpha. What other thing? Is negatively charged is an electron for a minus 1. It is more penetrating than alpha. What did we say about alpha? So I can just say the opposite.
Less penetrating.
So it's more penetrating. It has a positive charge of 2 plus, so this one has a negative charge. Okay, so all right. So this has a negative charge of 1 minus for a beta minus. Okay, it has a charge, so it is also deflected in a magnetic and an electric field. Read what I wrote for number 4.
It is deflected in an electric and magnetic field.
Because it has a charge. This is because it has a charge. What's its charge again?
Minus.
By the way, so that I don't leave this without emphasizing what I mean by deflected. If you have an electric field like this, such that the upper plate is positively charged and the lower plate is negatively charged, if an alpha particle enters, how will it be deflected? How will the alpha particle be deflected when it enters into this electric field? Are you listening to me?
Yeah, I just tried to get
If an alpha particle enters this electric field, how will it be deflected? You need to know, how will you know that? If you need to know the charge of an alpha particle, what's the charge? 2 plus.
2 plus.
So how will it be deflected when it enters into this field? which direction of the plate will it go to the positive side or the negative side? That's what I mean by deflection.
Positive.
It's positively charged. Opposite charges attract.
Yeah.
So it will be deflected in what direction?
Negative.
So an alpha particle will be deflected towards the negative side of the field because an alpha particle is positively charged. How about beta? How will beta minus be deflected?
We're going to a positive one.
Okay. In fact, an alpha will experience a bigger deflection because it has a bigger charge, 2 plus. This is minus 1. This beta minus will deflect towards the positive side by attraction. Minus is attracted to plus, so beta minus is deflected to the positive plate, while alpha, which is 2 plus, is deflected to the negative plate. So they all get deflected in an electric field and also in a magnetic field. Please, is that clear?
Yeah.
Very, very quickly. Gamma ray. Gamma is a ray. In a sense, it is not a particle, it's an electromagnetic wave. I'm on the next page.
Yeah, I'm on it.
So gamma is emitted when gamma is an electromagnetic wave emitted usually after an alpha or a beta decay, as the nucleons. Nucleons are the things you have inside the nucleus. Nucleons, or the unstable nucleons, as the unstable nucleons try to rearrange. Read what I wrote.
Gamma is an electromagnetic wave emitted usually after an alpha or beta decay, as the unstable neutrons try to rearrange.
So as they try to rearrange, gamma ray is emitted. Gamma is an electromagnetic wave, just like radio waves, microwaves, infrared, or visible light, or the red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, and gamma ray. They are all electromagnetic waves, and they are all transverse waves. Gamma is the only electromagnetic wave that is also a radioactive ray, a radioactive, radiation. Okay. See, gamma is the most penetrating. Should I talk about the characteristics quickly?
Yeah.
So can you give me the characteristics of gamma? It's usually the extreme case.
Most penetrating.
It's most penetrating. Any other thing you know?
Is it the least ionizing?
Is the least ionizing. You remember what ionization is? When it knocks out electrons from atoms in its way, causing those atoms to become charged. That's ionization. Least ionizing
Has no charge.
has no charge and has no mass and no mass. Though at the level of atomic physics, you can think of it as having a mass. Number 4, it has no charge, so it is not deflected. It is not what?
Deflected.
In an electric field or in a magnetic field. It is not deflected at all. And I also wanted to tell you that an alpha is produced when a gamma ray is produced or 2 photons of gamma. Let me just 2 photons. A photon is a unit of energy. 2 photons of gamma are released or produced, if you like. Okay, I need to zoom this in to capture it properly. 2 photons of gamma are released. 2 photons of gamma are released when an electron collides with a positron. Remember, a positron is the positron. A positron is the antiparticle of an electron. It's an electron with an opposite charge. And both of them get annihilated. Read what I wrote in yellow.
2 photons of gamma are released when an electron collides with a positron and both of them get annihilated.
Yes. Okay, I won't go too deep into that. All right. By the way, go to the previous page. A beta particle is less ionizing than an alpha particle, but it is more ionizing than gamma. Which one is the most ionizing?
Alpha.
Least ionizing is what?
Gamma.
Gamma. Most ionizing is alpha, least ionizing is gamma. Beta is in the middle of the pack.
Wait, beta is less ionizing than more?
Beta is less ionizing than alpha, but beta is more ionizing than gamma. Does it make sense?
Yeah.
Beta is just in between. In fact, beta can be I told you beta is more penetrating than alpha, but it's less penetrating than gamma. Beta can be stored by about 3 millimeter thickness of aluminium or metal. About 3. It can pass through what?
Can it pass? Did you say it can pass through aluminium?
Yes, just a small thickness of aluminium, about 3 millimeter or thereabout. About 5 millimeter thick aluminium or any metal, it can pass through. But anything bigger than that, it can stop a beta. Did you hear that?
Yeah.
An alpha particle cannot even go very far. A few centimeters of air will stop an alpha particle. A small thickness of paper can stop an alpha particle. But for a gamma is the most penetrating. You remember?
Yeah.
A gamma is never completely stopped. It's just that the intensity can be reduced. To reduce the intensity of gamma, you need to use what? A thick lead or concrete. Did you hear what I said?
No.
To reduce, okay, I first of all said that gamma is never completely stopped because it's highly penetrating. It's never completely stopped by any matter. It's highly penetrating, but you can reduce its intensity when you block it with a thick concrete or a thick lead. Did you hear that?
Yeah.
So where radioactive substances are stored, they are covered with a thick wall of lead or a thick concrete, so that if gamma is coming out, its intensity will be reduced. Because those things, when the body is exposed to too much radiation, it can cause cancer. It can cause mutation of the cells, which of course can lead to malignant growth or cancerous growth. I hope what I said made sense.
Yeah.
So back to the questions so that we can summarize it here. Look, go back to that question where we needed to review. That's is B.
Yes, it's
Figure 7 point this represents what? A decay that can happen inside the nucleus. Remember, this is a proton
yeah.
that changes to a neutron, and this gamma, this beta. This is actually a beta.
Oh, yeah.
So, can you hear me?
Yes.
Is a beta. Is a remember, this is actually a beta minus, by the way. A beta plus. If I is a beta plus, I need to let me draw your attention to it so that you see it. See what I said about beta plus. Go to page 11. Go to page 11. Are you on page 11?
Yes.
For a beta plus, one proton changes to a neutron, a positron, which is a positively charged electron, and a neutrino. So it's a proton that changes to a neutron and the other ones. So this thing has to be a beta plus. The question we are attempting. If you can go back to that question, you see it's a beta plus.
I thought you said it was a beta minus.
I said so.
Yeah.
I must have said that in error. Because obviously it's a proton that is changing to a neutron. So it's a beta plus. The answer is a beta plus.
Wait, so when it's beta plus, a proton.
A beta plus is when a proton changes to a neutron. That's what I drew your attention to on page 11. See it, page 11. A proton changes to a neutron. Then positron comes out, which is a positively charged electron, and then a neutrino. Then a beta minus, that's on page 10. Go back to page 10. A beta minus is when a neutron changes to a proton with an electron released. This electron is a beta minus particle.
Yeah.
And then an antineutrino. I think this is clear.
Yeah.
Okay. So you're good with this explanation.
Yeah.
Okay. I'm trying to remember when we did radioactivity, if I mentioned all this activity, half-life and all that. I think we've done that because this question is about radioactivity. Okay. Says the half-life of cobalt-60 is 5 years. A school cobalt source had an activity of 38.5 kilobecquerel. BQ is the unit of, yes, activity. Actually, the SI unit of activity, becquerel, in the year 2000. Estimate the activity of this source in the year 2020. That's after 20 years. The half-life is 5 years. What's half-life? Well, you have an idea. Half-life. Half-life. Think about the term half. The half-life is the time taken for the activity to become half of its initial value. The time taken for the activity to become half of its initial value. You can actually define half-life in two ways. It's also the time taken for the number of undecayed nuclei to become half of its initial value. Could you write it down so that you remember? You can just write it down in this space. We do the workings here. Half-life. Yeah, half-life, the time taken for the activity to become half of its initial value. Okay, please, you can also define it in terms of undecayed nuclei. So it's also the time taken for the number of undecayed nuclei to become half of its initial value. Okay, just put it in bracket. The time taken for the activity or the number of undecayed nuclei. So just put in bracket number of undecayed nuclei to become half of its initial value. All right. So, for instance, if at the start of the experiment, the activity was 80, right? 80 becquerel. Assuming at the start the activity was 80 becquerel. If after 2 hours, the activity becomes 40 becquerel, what's the half-life? Did you hear me? So I said at the start of the experiment, the activity was 80 becquerel. After 2 hours, the activity became 40 becquerel. What's the half-life? Remember, can you in 2 hours? Yes, 2 hours, because half-life is the time taken for the activity to become half of its initial value. It started with 80 becquerel, then after 2 hours, the activity is now 40 becquerel. So the half-life is that time taken for the activity to half itself from 80 to half 40. The time taken is 2 hours. So 2 hours is the half-life based on the illustration I gave you. So now, in this question, what are we told is the half-life? Five years. So it means after 5 years, the activity will become half of its initial value or original value. So can you do? You get it now. Beautiful. So work it through until you get to the year that we are talking about now. Not necessarily, but okay. Is the answer given in a different unit? The answer is still in becquerel. It's still in kilo. It's still in kilo becquerel. So you don't need to do any conversion. Are you supposed to divide by 5? Are you sure? Exactly. You should divide by 2. Because 5 hours, 5 years is the half-life. So after 5 years, the activity, it doesn't matter. Three significant figures is fine because the original value is given in, yes, three significant figures. Okay, so this is cool. After 5 years, it halves from 38.5, it becomes 19.25. After another 5 years, it halves again to 9.625. After another 5 years, it halves to this, and another 5 years, it halves to this. Have we exhausted the 20 years between 2000 and 2020? All right. So 5 years, 5 years, and 5 years. Another 5 years. So we have the whole 20 years from 20,000 to 2020. 20 years altogether. All right, that's fine. So 2.41 becquerel. Please, this is just a simple way you can do this. If it is given as a graph, you can actually read off the half-life from the graph. Let me see if I can sketch something to illustrate that before you move away from this. It's always good that once we're looking at a topic, we look at other things around the topic. So that it can be given in form of a graph, right? Okay, if it's plotted this way, let me see if I can make this neater. Just a moment. Activity can never be zero because you always have half of something until infinity. You know, you want to check that out. There will always be half of this last 2.41 and half of what you got from halving 2.41, and then another half again, another half again. It may be so small that it will never be zero. That's why the graph will be approaching the x-axis but will not touch it. So it forms what we call asymptote. Did you get that explanation? Okay, by the way, this is the y-axis is the activity or number of undecayed nuclei. So I will just represent it with A, activity. Then this is time. Assuming I have, it started with an activity of, let me use this one I was using as an example. It started with an activity of 80. Then at 40, let's say this place is 80. Let me arrange this. 0. 20, 40, 60, no. 1, 2, 3, 4, 5, 6, no. I have to graduate it better. So let me do 20. It's not well spaced out. So this could be 20, 40, 60, 80. Okay. So by the way, that's the activity is 80 at time 0. This time 0. So assuming at 60, this is 5, this is 10. Just a moment, let me write this to you. I think I need to zoom this thing out properly. 200 so I can capture this properly. Just a moment. So 5, 10. Okay. Hold on, let me just, okay, 20, 40, 60, 20, 40, 60, 80. What's the half-life of this particular radioactive substance that are represented in this curve. Can you figure out what I've drawn? So what's the half-life? What's the half-life? Assuming this time is in hours. Are you sure it's 5? Let's say this, or I can say the time is even in seconds. So that's a very short half-life. Activity in becquerel. So what's the half-life? This is how you check. When it started at time 0, what was activity? So how long did it take the activity to halve itself? Pardon? No, how long did it take the activity to become half of its initial value? Are you sure it's 5 seconds? At 5 seconds, the activity is 60. 10 seconds. So what's the half-life? 10 seconds. So when you look at the graph, you start with a particular value, for instance 80. Then you check out how long does the time that passed for that activity to become half. If it took 10 seconds for the activity to become half, that's at 40 now. From 80, half of 80 is 40, and it took 10 seconds. So the half-life is 10 seconds. Okay? Sorry, is this clear? Yeah. Let's go to the next question.